Hello and welcome to the first of two quick learning sessions about driving inductive loads with power MOSFETs. My name's Keith Heppenstall. I'm a concept engineer with the automotive power MOSFET team at NXP. Power MOSFETs have a virtually infinite power gain, so they're very useful for driving large high current inductive loads from very low level signals such as those from a microprocessor. MOSFET circuits can be adapted to provide the current waveforms needed for lots of different types of inductive loads. You're probably all familiar with the textbook circuit that you normally see of a low side MOSFET driving an inductive load. This load has got a 1 ohm resistance and some inductance. And it's got a freewheel diode, which is normally seen in the textbook circuits. The power MOSFET is turned fully off when there's 0 volts on the gate, when the gate source voltage is 0, and to turn it fully on, you need to put 10 volts on the gate relative to the source. So when this MOSFET is turned off, when it's turned on, a current flows. You have 12 amps of current through a 1 ohm resistance with 12 volt battery. When the MOSFET's turned off, the current which was flowing through the MOSFET, the inductance wants to maintain the current, so that current then flows through the freewheel diode. So the voltage is very low when the MOSFET's turned on. It's less than a volt. When the MOSFET's turned off and current is forced through the freewheel diode, that voltage rises to about 13 volts. There's about a volt drop across the freewheel diode. And when the current's fully died down, that voltage will go down again to 12 volts, the same as the battery voltage. Okay, now freewheel diodes are very good because they prevent this voltage from getting very much higher than the supply voltage. However, they do have one or two disadvantages. First of which is they cost money. So if you can avoid using a freewheel diode, it's one less component on your board, and it's more reliable because that component's not there. The other problem with the freewheel diode is if your supply becomes reversed for any reason, and it does happen, then the body diode of the MOSFET and the freewheel diode form a low impedance path, and you get a very high current, and you will destroy either the MOSFET or the diode or both. The other problem with them is if you have the freewheel diode, the rate of decay of current in the inductive load is very slow. You don't have much voltage across the load to cause the current to decay, and the decay rate is very low, and so you have a slow dropout rate if you're driving a solenoid. So what can we do if we get rid of it? Another way of clamping this voltage, if you're worried about the drain voltage of the MOSFET becoming excessive, is to use an active clamp. So similarly to before, we turn the MOSFET on, current flows through the load and through the MOSFET. When that load is turned off, the drain voltage starts to rise. When the drain voltage rises to a voltage that's sufficient to start this Zener diode conducting, we've got a 40 volt Zener diode here. When that diode starts to conduct, it actually drives the gate of the MOSFET, so it holds the MOSFET in conduction. So if we look at the response on the safe operating area curve, which you can find in the data sheet, this is where the MOSFET's off, and there's a very low current, and the voltage is 12 volts. When we turn it on, it goes up to this point here where the voltage is very low, but the current's gone up to 12 amps here. Then when you turn the MOSFET off, the operating point of the MOSFET goes from this very low voltage here to the voltage here, which is determined by the Zener diode and the MOSFET threshold voltage. So that goes up to about 45 volts. So that puts a much higher voltage, a much higher reverse voltage across the load. The current dies down much more quickly than it did in this case here. So the current it dies down quickly to a very low level. Then when there's very little current, the Zener diode is no longer conducting current, and we return to the off position. Okay. Now this point here, when the MOSFET starts to turn off, is really quite a high power. We've got 540 watts in the MOSFET. So that will tend to heat the MOSFET up very quickly. So you've got to be very careful with the size of the MOSFET compared to the inductance and the voltage that you're operating it at. You've always got to maintain that point there so that it never overheats. So you've got to maintain the die temperature at less than 175 degrees centigrade. Okay. The situation if you remove these components, these clamping components, you avalanche the MOSFET. So the MOSFET's turned on and off as before. The load current wants to continue to flow because it's an inductive load. The current, instead of having a path through that turns the MOSFET on and maintains it in conduction, this current breaks down the body diode of the MOSFET, so the MOSFET avalanches. In this case, the operating point is much further out than before. It goes beyond the rated voltage of the MOSFET. Here, this particular MOSFET is a 55 volt MOSFET. The voltage goes up to about 1.3 times the rated voltage, so it goes up to about 72 volts. The MOSFET breaks down, but it's not destroyed. It's not a catastrophic breakdown, and the MOSFET body diode conducts the current, and the current dies down very rapidly. When the current can no longer sustain the breakdown voltage of the MOSFET, when the current's died down to, say, a milliamp, then the operating point returns to the off position here. There is a significant difference between active clamping and avalanche, in that active clamping, the MOSFET actually has a negative conduction coefficient, temperature coefficient, which can tend to produce thermal instability, whereas the avalanche situation, the MOSFET avalanche voltage has a positive temperature coefficient, and this tends to prevent the formation of hot spots, so it's a thermally stable situation. So we've seen now how power MOSFETs can form a cost-effective and versatile interface between signals and high power loads that they drive. The reliability is excellent if they're operated within their specified safety limits. The most important safety limit being the maximum die temperature, which is 175 degrees centigrade. If you need more information, please go to nxp.com/MOSFETs. Thank you for your attention, and we'll see you shortly for the next part. Thank you very much. Goodbye.